Okay, hi everyone. Today we're going to have a look at Kubernetes workflows for open infrastructure, where things are today and where we think they might be going tomorrow. So just by way of introduction, my name's Pete Burley. I've been working with Kubernetes for quite some time for infrastructure management, and I currently work on OpenStack-Helm, as well as looking after lifecycle management for quite a few projects within AT&T's Network Cloud and Airship.
I'm Alan Meadows. I'm a lead cloud architect for Network Cloud at AT&T, and I work within the Airship and OpenStack-Helm communities.
Steve Wilkerson. I've been at AT&T for about 4 years now. That 4 years I've been working with OpenStack exclusively. 2.5 of that has been spent on working with OpenStack, running with Kubernetes.
Okay, so I think one thing that's kind of quite important to note at this stage is although we all collectively work on both Airship and OpenStack-Helm, this is not the direction that either of these projects have definitively decided to go on at this stage, although obviously we're quite strong proponents of this. So this morning, some of you may have attended the lessons learned running open infrastructure on bare metal Kubernetes cluster in production, where we describe some of the wonderfully exciting and sometimes perplexing issues that can hit you when you're breaking all the standard advice for running Kubernetes-based clusters. And a brief tour of Twitter, from a couple of years ago, provides some really sort of key, pertinent, and accurate pieces of advice. Essentially, don't attempt to run stateful applications on Kubernetes. Don't run applications that interact deeply with the host on Kubernetes. Don't treat your infrastructure as pets under any circumstances. And where possible, try and write and run proper 12-factor applications that are self-contained, looking after their own, potentially very short lifespans and are highly fault-tolerant. And there are kind of two ways of looking at this bit of advice. Either it's a pretty good set of rules to live by, or alternatively, let's sort of disregard that and run OpenStack, Ceph, Galera clusters, VNF workloads, and sort of really sort of try and build resilience into applications and how we manage them. And so we chose the latter option, and sort of through the experiences we had there, haven't really regretted it. We overcame a lot of hurdles along the way to what was eventually the Airship 1.0 release today. Okay. And our journey to Kubernetes open infrastructure essentially began with OpenStack-Helm. At its heart, OpenStack-Helm can be viewed as the marriage of Kubernetes, Helm, and OpenStack that seeks to create Helm charts for each OpenStack service. And these charts are designed to provide sort of hermetically sealed units for complete lifecycle management for their services. And we sort of went beyond that initial goal for instantiating OpenStack services, and we hope that it continues to provide an incredibly customizable framework for operators and developers alike, which allows people to deploy, maintain, and upgrade a fully functioning OpenStack environment and their supporting infrastructure for both simple and complex environments. And by and large, this has really delivered on its mission for us. However, fairly early on, it was apparent that it was only a small part of the picture. And if we were to unlock the advantages of declaring state for our infrastructure, we'd need to go quite a lot deeper.
Yeah, so the ability to declare up front all of your infrastructure as configuration is really at the heart of what we were trying to do with Airship. In a lot of ways, we were ahead of our time a little bit. So the vast majority of Airship was built from the ground up to expressly provide this configuration-driven infrastructure. So mostly because no comparable and already available community option existed. So to be sure, some clear winners in the general upstream community space have started to emerge for some of the areas that Airship cares for. And in some cases, it makes sense for Airship to transition to those to start leveraging them to build on a more common, platform than to maintain it all on our own. So for instance, declaring the desired state for bare metal provisioning, that was the whole intent behind Airship Dry Dock project, and much like much like the cluster API work that's now starting to gain momentum, and the work that's occurring in Metal Cubed and stuff like that. Similarly, Promenade was really born out of the need to have a configuration-driven approach to deploying highly available Kubernetes clusters, while kubeadm was really still using at that time an imperative approach with limited capabilities for HA. And clearly, kubeadm has come a long way since then, and working towards incorporating that as an installation mechanism just makes sense now. Well, really, at a higher level in the stack, our configuration management system, Deckhand, and its partner, Pegleg, were built to holistically solve the problem of managing configuration for multiple sites at scale, solving really similar problems to what Kustomize is now trying to tackle with things like overlays and substitution. So where we really kind of failed, though, was ensuring that our workflows themselves were equally configuration-driven. So we initially chose Airflow as our workflow engine because of its wide use as a DAG workflow engine, and tried to make as much of the workflow configuration-driven as we could, but ultimately, with the technology choice, we could really never open it up as much as we wanted to for operator control. And really, this is necessary to account for not only bringing your own declarative workflow, but also handling more complex workflows, things like dealing with complicated upgrades, things like trying to upgrade Kubernetes and Docker at the same time, all part of some sort of declarative approach.
Okay. So the transition to declarative infrastructure, where we explicitly define our desired state for our entire data center, from physical topology through the operating system, deployment and configuration, down to up to the software that is expected to run on top of it, has paid huge dividends in terms of the ease which we're able to lay out and specify how we want our infrastructure to operate. And these have come primarily from the following factors. One, it's really easy to digest. The declarative model simplifies writing system configuration, provides a more natural way to understand how those systems are configured. It's fairly simple to just kind of look at, choose YAML as an example. In this model, you can lay out how you expect the configuration for your infrastructure to look, and it should be pretty self-explanatory as long as you're using a simplified model for that. Also, declarative infrastructure makes day one operations pretty awesome, at least in my opinion. As long as our configuration matches the models for our system, we can usually go and grab coffee and simply watch the console or tail log files for something that's operating, while the underlying software takes care of the heavy lifting for us. And also, simple day two operations can be just as awesome. Simple changes can be achieved by simply updating our infrastructure configurations and triggering an update while we go and refill our coffee. You want to talk about some of the downsides, though, Pete?
Yeah, we do more than just drink coffee while we're deploying this stuff.
Although there's a lot of coffee.
So, I mean, as a result of the advantages that Steve has mentioned, it really kind of is where we started to more think of infrastructure as configuration rather than infrastructure as code, which kind of touches back to what Alan was saying about where we felt we could potentially go even further than we have to date. Because we've had some drawbacks with this. Essentially, if we're trying to make a really deep and meaningful change to the way our infrastructure is laid out, which could be potentially as simple as adding something like the new Nova placement API, or removing other services from where we are, then it gets pretty hard to orchestrate without some sort of conditional logic or branching structure in place. Additionally, it can be sort of pretty tricky for us to insert dynamically logic that allows us to recover from an unhealthy state, where we might end up with a sort of a series of mops building up that allow us to perform actions on the site. And also, we find sort of introspecting where we were in the particular phase of a deployment or another activity quite hard to do. And the tooling that we have gives us a really good declarative control over that flow, but sort of trying to identify either how fast we're going or where we are at any particular point in time has proved difficult for us. So As a result of these things, we've ended up with this large number of ad hoc mops that perform part of our upgrade, maintenance, and reconfiguration process, as opposed to having a single unified entry point for all operations that cater for every potential stage at the life cycle of a site as our target state.
So these mops that Pete is referring to, in order to perform these very, the times that we use these complex mops, effectively to do these sort of complex upgrades, like we were sort of referring to, whether that's leaping in a Docker version or Kubernetes version simultaneously, doing complex, maybe OpenStack leaps at the same time. We found ourselves going around the declarative system that we had sometimes, or stepping outside of it. And this has really been the source of our learnings in this space. So really, rather than just admit defeat and create a mechanism for us to do that, we actually wanted to look closely at all the points that we found ourselves circumventing the declarative system and come up with a way to actually support that declaratively. So we really wanted to be able to define any sort of scenario, no matter how complex, declaratively, and leverage that with this platform. So it was our opinion that this wasn't really a failing of the infrastructure configuration or declarative model, and rather it was that we didn't really have the right tool set or the right exposure to control how you manage these updates for any given upgrade.
And so, from this stage, from our perspective, it's fairly apparent that we need to be able to define our path from A to B at any point in time, because often either for business, technical, or other constraints, we need to go through an arbitrary point C along the way, and merely defining our end state won't suffice. And I think it's important to be clear that we're under no illusion that this is sort of some profound epiphany that came to us alone one night, and that the community is now working on several approaches to this problem. And these range from the most rudimentary, for example, adoption of existing technologies such as Ansible to help manage the deployment and management of Kubernetes workloads, through to really sophisticated operators that extend the Kubernetes API with new objects and can perform very complex management tasks via purpose-built controllers deployed within the cluster, offering a really good user experience.
So as Pete mentioned, really given we weren't alone in this space, in terms of looking for a solution, we also really didn't want to reinvent the wheel. So we wanted to look at what others were doing, and we wanted to build this workflow processing approach from the ground up to function in a native Kubernetes environment. What we mean by that is that typically our workflows today, they potentially involve touching the very things that are helping to drive those workflows, or the dependencies that the workflow engine depends on. And this creates a real challenge for us for treating any kind of update exactly the same. So in other words, when the update actually touches the thing performing the update, it becomes sort of an outlier, and that's when we end up needing to sort of step outside the declarative system. We want to avoid that. So we rule out obvious tools like Ansible, because we really strongly believe that a critical aspect of what the workflow orchestration tool will do is release management, and we really don't want to use a configuration management tool to drive release management. We looked at operator patterns to help us accomplish these complex workflows, and really, while some targeted and scoped operations are the obvious correct choice, for instance, Rook to manage Ceph, operators, they can require a heavy investment in order to create them. And all the subsequent updates to the operator to handle each and every new small workflow might be overly complex for what we're trying to do. So in other words, operators made sense to us when you are ready to make a large commitment to a scoped area of management like Ceph, but really not for ad hoc configuration-driven workflows. And so ultimately, we wanted to ensure that we align with the very goal that we set out at the beginning, which is to achieve infrastructure as configuration. And so we needed a cloud-native workflow product that can handle defining how a site is deployed, but just as easily leverage customizations to how a site is updated from release to release. So we looked at the landscape for cloud-native workflow engines, and we came up with 3 possible contenders. And digging into each of them in more detail, we had to figure out which one was really ready to do declaratively defined workflows ranging from bootstrapping a site to handling day 2 operations in that site and handling complex infrastructure upgrades, all driven by configuration-based workflows with the fewest possible dependencies. And so we evaluated this from a few different perspectives. Can it support DAGs? Does it support linking internal, external objects and events and also configs? And how does it function from an operator perspective?
So for this, there were sort of 3 primary contenders that came to the foreground, and we can sort of run through each of these just now in terms of how they're pitched. So the first one we looked at, Mesosphere's Kudo, which was previously known as Maestro, is a fairly low-level tool which introduces 4 new resources into our Kubernetes environment. Frameworks which provide a high-level description of an application, e.g. something like MariaDB. Framework version, which describes the particular version of an application, e.g. which version of MariaDB or Galera it is we want out there. Instances, which are the realization of that framework version. They stick around throughout the application's entire lifecycle. And plan executions, which describe the various executable actions to take for any particular workflow. And in its current state, a user of Kudo doesn't interact directly with plan executions. Instead, they deploy a plan execution. The deploy plan execution is created along with an instance. And Kudo is very much still in its infancy, so further interaction with plan executions will probably emerge down the line, although at this point it's really kind of too immature to meet our immediate needs. And so the next engine we looked at was Tecton Pipelines, which also provides 4 resources specific to the workflow. Tasks which describe a particular action. It's kind of analogous to an instruction. Run tasks, which are the resources used to trigger that task. Pipelines, which describe a series of tasks, the order in which they should be run and how they're interlinked with each other. And a pipeline run, which actually kicks off that pipeline. So rather analogous to sort of a task run to a task. And additionally, there's a 5th CI/CD focused resource called a pipeline resource, which represents the artifacts such as Git repositories or Docker images that can be used as the inputs and outputs to a workflow. And then finally, coming on to Argo, which is the most mature of these projects and takes a slightly different approach focused upon operator friendliness as opposed to Tecton, which is very heavily focused on CI/CD objects and infrastructure. So as a result, we only get one CRD with it, the workflow, which acts like a combination of the pipeline run, and associated tasks from Tecton. So as soon as we introduce this CRD into Kubernetes, it immediately kicks it off, and the execution flows through each task as described by the workflow, which gives us a more direct approach to lifecycle management, while also letting us use the declarative approach to describe the resource.
And just to sort of repeat again, what we were looking for out of this choice is really a unified way for us to achieve these deployment instantiations of resources in the site, handle these reconfiguration of those resources or upgrades, and finally, the restoration of critical services automatically when things fail, much like the backing up of MariaDB and restoring it when some sort of upgrade failed. So when we looked at OpenStack-Helm, for example, we have the ability to do these things as jobs, defined in the charts, but we end up with a very rigid set of functionality that's supported that cannot be configuration driven. So instead, we foresee engines like this helping us to perform these sorts of database backups prior to things like OpenStack upgrades, and helping us roll those back when there are failures. So the ability to perform these conditionals or certain configuration-driven paths for workflows to go down, and the ability to dynamically build workflows from runtime data in the site, and the ability to augment these workflows with minor changes from one release to another was really something that was critical for our needs. And so we wanted something that could provide a simple operator-centric view into what was going on in a workflow and easy controls to pause, retry, and resume workflows.
Okay. So, as Alan just touched on. I mean, all three frameworks offer very similar basic functionality and the ability to execute simple parallel workflows. However, for us, having the ability to running DAGs, which interact more directly with other things going on in our cluster is pretty important to us, as we want to be able to allow both the easy insertion of extra logic, where a developer only needs to define the required starting state for any additional steps, and also we want to be able to loosely specify our workflows, allowing the executor to both dynamically build and determine the correct ordering of tasks within them.
So in addition to what Pete and Alan were talking about, we also evaluated the ability to pass parameters amongst these tools. For workflows to really add value to the end-to-end lifecycle management that we're looking for, we really require the ability to pass parameters as arguments to these workflows. These parameters can be configuration values that have been declaratively defined, or arguments for the executed command in a workflow step. But ultimately, this allows us to pass arguments to the entry points for the workflows that can be tied to events that occur during the life cycle of our infrastructure. And as you can see, the three workflow engines here that we're speaking about meet this criteria. In addition to passing parameters, we also evaluated the ability to pass in Kubernetes resources. In some situations, the ability to manage Kubernetes resources as part of your workflows can provide additional value and flexibility through the lifecycle of your application. An example of this could be passing in the manifest for a job to execute as part of your workflow that doesn't necessarily need to be managed beyond kicking it off and letting it run to completion. And you can see Argo and Tecton meet this criteria, but Kudo does not. In addition to passing resources, we also looked at support for hardwired resources, things like Git, S3, for example. Support for these hardwired artifacts allow for easier customization of our lifecycle workflows because we can declaratively define these resources through configuration. To give you an example, if we want to execute a workflow that interacts with an S3 bucket, we can leverage native configuration for these hardwired resources to define the S3 endpoint that we want to work with, the access and secret keys for the user that we're attempting to access this endpoint with, as well as the bucket that we want to interact with. The ability to interact with these hardwired resources allows us to define workflows that interact with both internally and externally generated resources. As another example, we could leverage a Git hardwired resource in a workflow that triggers from an event such as an upstream or downstream merge to a repository. And once again, Argo and Tecton check this box, but Kudo does not. And finally, in addition to the hardwired resources, we also evaluated these workflow engines for secret and volume compatibility. Secrets compatibility was the ability to interact with Kubernetes secrets provides value in that we can leverage these secrets that are created either by our workflows or from other aspects of our infrastructure lifecycle. Using the previous S3 example, a workflow could install a Helm chart that includes a template for a secret that defines an S3 user and their associated access and secret keys. The idea being that a workflow could then consume that secret to bootstrap the user in S3 and link the secret and access keys to that user's UUID. Once again, Argo and Tecton check the secret compatibility box, while Kudo does not. In addition to secrets, the ability to dynamically create and use Kubernetes volumes in our workflows allows us to move data between steps in those workflows that may require persistence throughout the life cycle of the workflow. In such a scenario, if we're just using it to pass data between workflow steps, we would expect to be able to destroy that volume upon the completion of the defined steps for that workflow. But in addition to dynamically creating volumes, we also looked at the ability to consume pre-existing volumes in executing our workflows that may need to operate on data that we expect to exist before our workflow begins and after it completes. And once again, Argo and Tecton check this box, but Kudo did not.
So in this slide, we're going to introduce a new icon, which is the bang that you see up there is effectively not that it's not supported, but that it is on the project's roadmap. So we wanted to be fair to the future things that are being planned and are directly on that component's roadmap. So these items all fit into a particular bucket, and that is the perspective here is whether this workflow engine is capable of handling the needs of operations type folks leveraging the workflows that are coming out of development. So in terms of conditional branching, going back to what Pete said earlier, despite our declarations, a given site may not always be in the state that we've declared as our intent when we actually start a new workflow. So we need the ability for workflows to adapt in real time, based on obviously previously declared possibilities, to adapt to a site that's slightly less optimal or air out early for sites that are too sick to perform operations on. We wanted the ability, obviously, for range-based loops. So, loops and can be dynamically created based on the results of some previous workflow step are really an essential element to the sort of thing we're doing with these complex changes. So an example of this would be a step that goes out and gets the list of all the Kubernetes nodes as part of step 1, and step 2 could be that we actually want to do something with that list, like let's say create a pod for each of those Kubernetes nodes that's specific and scheduled to it and actually does some sort of change on each of those nodes. And the workflow would also give us back the success and the failure of that operation for each of those individual nodes.
That might have made some Kubernetes upgrades easier.
Yeah. So recursion, so the freedom of one workflow to call another, even itself, allows us to build complex workflows. So, for example, recursion allows us to construct a workflow that can loop or retry until they get the response that they want or need before continuing. And they can continue to keep calling back into themselves until the right conditions are met. Timeouts are really critical because things don't always go perfectly. So obviously there's some steps that we want to perform, but they might not happen in a reasonable amount of time, and we need some way for the workflow engine to basically say this is not going to happen, this is taking too long. And retries, similar to the above, again, this is an operations type perspective. Sometimes things don't work, and we want the workflow engine to be smart enough to pick up where it left off, have an easy interface for operators to go ahead and trigger a retry, and to have that really be a first-class citizen in the workflow engine.
I suppose the other side of retries is having separation of instructions and actions, which allow us potentially to sort of separately define the actual workflow itself and when we want to run that. But as I touched on earlier, this is probably less relevant for us, simply because we view a Helm chart as the sort of unit of packaging that we operate within Airship managed clusters. And so the sort of canonical entrance point for performing any action is via Helm install or Helm upgrade as appropriate. The other thing we want to be able to do is allow us to suspend, i.e. sort of pause and resume workloads, which is particularly useful during development, but also if some operator wants to intervene at any particular stage for any reason that they have. And then exit handling, where currently, although Tekton has some stuff in its roadmap, Argo supports really rich error handling, which when combined with the DAG allows us to build out much more intelligent responses to execution failures. For example, rolling back database migrations or performing some sort of remedial steps for an unhealthy service. Currently, for notification sending, only Tekton has this in its roadmap, although as an explicit object or item. But ideally, we'd like to see some hooks that allow us to easily emit notifications to both CI systems and operations teams, both at the end of a particular workflow's operation, but also potentially upon reaching different states and stages within the execution and signaling to external systems.
So, looking at these three options that we evaluated, we struggled over whether we should place effort into Argo or Tekton-based workflows. I mean, those are really the two choices on the table. And while we appreciated the great work that Google and others are putting towards Tekton, its mission statement as a CI/CD building block really has us wondering whether it really ever truly will support a more operation-centric feature set. So in other words, even when it does start to check boxes in our evaluation matrix, will they be more oriented towards building a CI/CD based workflow or operations-driven workflows? Couple that with the fact that it's clear from the comparison that if we want to start this transition in Airship today, which we do, then the technology that has the largest set of features we need right now is clearly Argo. So in the end, we think that the largest effort of moving this direction is making the move initially to one of these configuration-driven engines, and in the future, if Tecton does become some sort of clear winner, the transition at that point is simply to change YAMLs from one format to another, from Argo to Tecton.
Okay. So I think at this point it's probably worth demonstrating how some of these technologies work in practice. So we can use probably the simplest example from OpenStack-Helm of instantiating Keystone as to look at how this sort of stuff can start to affect how we manage the LCM of an OpenStack service and its future expansion potential. So Steve, would you like to deploy Keystone via the current version
Sure.
of OpenStack-Helm?
Okay, so we're going to see a few things here. The upper right-hand side, we're just going to execute a watch on the pods that we are going to deploy as part of this. So the dependencies we've already deployed, so things like MariaDB, RabbitMQ, and Memcached. The upper left, we've packaged the Helm toolkit and Keystone chart. And the lower terminal here, you'll see that we're essentially just trying to interact, just trying to call OpenStack endpoint list and issue a token. So now on the upper left, we're just doing a Helm ls, show what's already deployed, and then feeding some overrides to the Keystone deployment command. This is essentially just 3 replicas to show in HA type deployment, as well as defining a public FQDN for the Keystone service. So there's some things going on concurrently. On the right-hand side, you'll see we've got a DB init job, which is essentially going to set up the Keystone database and the Keystone database user. Keystone DB sync job that's going to perform the database management for the Keystone service, as well as there's a job for initiating the RabbitMQ user for Keystone. There's also a job that we run before Keystone to set up the credentials. And then, so now that the jobs have completed, we can see the Keystone pods are running, just waiting for for them to become ready and receive endpoints.
And it waits here just as it takes about 30 seconds or so for the HTTP probes to kick in. And we should now we start to see tokens coming through and an endpoint list. And should we maybe have a look at how, if we orchestrated this flow via Argo, that would look?
Sure.
Let's say the next one. Oh, sorry. So here we're going through essentially the same series of things. We've got some our existing infrastructure up and running. We've built the chart. We're now just waiting. We should start to deploy it in a second. So here we've also got Argo deployed in our cluster. And feed it the same set of overrides into our chart. This time when it's created, it will create a workflow, and we'll move over to start monitoring how that is progressing. So the very first thing that it'll do is just do a sanity check on our environment, check that the database is up and running and accessible, that we have cache there, and that RabbitMQ is up and in a healthy state. Once that's done, it starts to execute the tasks that were involved in bringing up Keystone, bringing up, managing Fernet tokens, setting up credential keys, setting up the initial database. You can see here as well that we've got an output parameter of db exists equals false, which will become relevant in a bit because we have no database to back up. And then it'll perform the same database sync or migrations to get us up and running. And in a minute or two, we should actually have, when that completes, we'll start being able to get tokens out of Keystone from this separate Kubernetes cluster. And again, here, unfortunately, it just takes a bit of time for all the probes to kick in and the ingress controllers to add endpoints. The other thing that we have here is a second workflow that allows us to perform any post-deployment actions we want. Typically, this would be doing things like setting up roles and any additional domains you want if you're interfacing with LDAP or something like that.
I think it's worth pointing on the right-hand side, you're seeing the out-of-the-box Argo CLI output there.
Oh, yes. Okay. Here we can see we started to get some tokens, and also the bootstrap job is completed, is running. Do you want to show the UI for Argo for this? So Argo offers both a CLI and a web-based GUI, where we can go in and sort of see exactly how this flow of tasks runs through, get logs at each stage in the process, and really picture where we are at the stage in the deployment. It also offers a Gantt chart type view that allows us to sort of hone in on where is really taking time in our deployment and view that dependency graph very simply. Okay, how are we doing for time?
Got about 5 minutes.
At this stage, I'm wondering if we should show the meta controller work that's been happening as well. Okay. That's a copy and paste file. So, something else that's been going on is we've sort of been looking at how we can combine these workflow technologies with the best that you can get out of systems like operators to provide both a really good end user experience for our physical operators, and also a good developer experience that allows people to get straight into the business logic. And so at this stage, I don't know if you want to come to the stage, Hemnath, with the work that you've been doing, which allows us to use Google's Meta operator project along with Argo to essentially produce a generic operator in 52 lines of Python, of which we have a very early POC that we'd like to kind of share now. Just hit play when you're ready.
Yep. Thanks, Pete. So we can see on the right-hand side the list of pods which are already running, and on the downside we can see the list of namespaces. And in this POC, what we are demonstrating is we are creating a custom resource called tenant, where an operator can define list of namespaces as well as resource quotas. So using a meta controller and using a custom controller, and also Argo workflows in turn will create the namespaces. So on the right-hand side, you can see already the Argo engine workflow controller as well as the meta controller is already installed, deployed. And then the workflows as well as the Argo workflow has been done as a config map. And this is the CRD of the tenant, where we can define the tenant CRD.
So at this point, we've added effectively a new endpoint to the Kubernetes API that allows us to query for tenants.
Okay. And then dynamically we can give the new controller or the tenant controller to the meta controller, again using YAMLs. Here you can see we have added that. And this is the tenant controller, where you can see the tenant controller came into picture, which in turn will talk with our meta controller, pass the Argo workflow, and Argo workflows will be created. Right. Now we are going to create a tenant just to show. So the operator have defined two namespaces, tenant1 ns1 and tenant1 ns2, and corresponding resource quotas. This is the definition by operator for the tenant custom resource. And then you can see a couple of Argo workflows have been started, which in turn will create the namespaces.
And that operator, the tenant controller image that is on the far right of the screen at the bottom, that did just take, about 50 lines of Python to go from a Jinja 2 templated workflow into something we could articulate in an operator-like fashion.
Right, you can see the tenant namespaces created and active. Now we are going to delete the tenant custom resource. So by deleting the tenant custom resource, the meta controller and the Argo workflow should be deleting all the namespaces as well as the pods it has created. So you can see the tenant namespaces are getting terminated and the Argo workflows are also getting terminated. Right.
Okay. Thanks, dude. So yeah, we're sort of pretty excited about the potential for combining these sorts of things in the future, for generating lightweight interfaces where it doesn't quite make sense to go down the same sort of path that you would take for something like Rook for Ceph management. Okay. So thanks everyone. Open for questions.
Sure. Any questions?
Yes, hi. Have you considered trying Mistral for the workflows? It might need a Kubernetes operator and some custom actions, but it seems like it would fit a lot of use cases you have for the workflows.
I think, you know, when we're evaluating these sorts of things, for us, we view Mistral as being an augment. So in order to do the same sort of level of interaction that we can do at the moment via Kubernetes, it would involve a very large and extensive amount of work to enable us to get this sort of visualization and interaction via kube control. And then you also have supporting infrastructure like MySQL, RabbitMQ, Keystone, and other things that make it a very heavyweight solution. And what attracts us to this is firstly its nativity to working with Kubernetes, but also how lightweight it is.
And it's not just the heavyweight element. It goes back to that point we were making, which is a lot of times we're using the workflow engine itself to update the things that are powering the workflow engine. So in other words, if you had to make updates to that underlying RabbitMQ cluster or Keystone that was helping power Mistral, you have a bit of a chicken and egg problem, and it just gets highly complex. So when we look at tools like this, things like Argo, they literally have almost no dependencies.
Thanks.
Okay.
Thank you.